Okay, let's get started. My name is Scott Teed. I'm a senior psychologist here at Stone Environmental. I will be moderating the webinar today. I also have a co-chair in Sebastian Castro, who is an Uber environmental modeler here. I'm going to take a moment just to introduce Stone Environmental for those who are unaware of the company. We are an employee-owned environmental consulting firm headquartered in Vermont with offices in Canada, Austria, and Germany. Our vision is to lead the development of innovative solutions that promote environmental sustainability. Our mission is we provide scientific tools, information, and analyses to help our clients solve environmental challenges with integrity, expertise, and innovation. And we are dedicated to a collegial work environment that fosters excellence, creativity, and accountability through employee ownership. So welcome. I'd like to introduce, this is our very first environmental systems modeling webinar of a series of webinars we hope to hold in 2024. We hope to have at least 2 more events that are planned with topics to be determined shortly. After the webinar, you will receive a follow-up of just 4 survey questions. One of the questions will be regarding which topics you would like to hear about in the next couple of webinars in 2024. If you can complete that and get it back to us, we would love to hear from you and get some feedback on the webinar itself today. So webinar dynamics. We will have the mics turned off currently, just because there are so many participants in the webinar here. We've got roughly 50 people signed up. We will turn the mics back on at the end of the webinar in order to have people ask questions directly. But during the webinar, please use the Q&A tab at the top of your screen to access the Q&A feature and type in any questions that you might have along the way. We'll get to those right at the end of the webinar. If you would like more information on today's topic or have any questions about our expertise in other areas, we would love to hear from you. Please feel free to contact us through our website or LinkedIn pages or directly using the provided email address that you signed up for on the webinar. The webinar is being recorded, and all materials, including Python scripts I hear, will be available for access and will be provided in a link in the chat box shortly. Sebastian should put that in there very shortly. So now on to our webinar. Our talk today is on machine learning for hydrology and water quality assessments using random forest for spatial extrapolation of streamflow metrics. The presenter is Dr. Jan Kiesel. He's an environmental modeler and hydrologist, and he's been with Stone since 2021. He's located in Germany and has extensive international experience, and he specializes in tailored software solutions that enable automated workflows, big data processing, and comprehensive uncertainty analysis in the fields of hydrology, landscape modeling, and spatial analysis. So with that, I'll turn it over to Dr. Kiesel, and please enjoy the webinar.
Thank you very much, Scott, for the introduction, and welcome everyone to our first webinar on machine learning with random forests. So the content is split basically in 3 sections. First, we will give a quick introduction to the topic, how to apply random forest, then for Streamflow metrics prediction, and finally wrapping up the webinar with some conclusions, a coding example. And we aim for about 15 minutes questions and answer session. So who am I? I'm Jens, environmental modeler at Stone. Scott already mentioned where I'm mostly working on, also including hydrology, water quality modeling, climate change assessments, and machine learning. So the aim of the webinar is basically to give you an introduction to machine learning, and so that you understand the capabilities and pitfalls of using random forests for predictions of streamflow metrics. We will also provide an easy-to-use code example, but basic Python knowledge is required. So starting with a quick overview of machine learning. So if we read the definition of machine learning, which is a field of study in artificial intelligence concerned with the development and study of statistical algorithms that can learn from data and generalize to unseen data and thus perform tasks without explicit instructions. So it means, first of all, and most importantly, we require training data for the predictions, and that it's generalizable, so pretty flexible in terms of problems that it can be applied to, and it works without explicit instructions, so it has no prior process knowledge for what we apply the machine learning algorithm. This definition that we just heard is logical and quite understandable, but structuring the field of machine learning into categories, learning problems, examples, and algorithms is not so straightforward. Many different approaches exist. Classifications, mind maps, and flowcharts overlap and sometimes contradict each other. So I decided to actually use a machine learning model itself to classify and explain machine learning in a hopefully a little bit structured way. So I provided down here some references for further reading and resources that are useful in my opinion. So roughly speaking, machine learning can be categorized in these three categories. Supervised learning, where we have known inputs and known outputs. Unsupervised learning, where we have known inputs but no knowledge what the output actually contains. So these are very hard to verify. And then we have reinforcement learning, so where the algorithm receives direct feedback and constant adaptation is required. So some examples for unsupervised learning are clustering and dimensionality reduction, which are basically simplification tasks or image or customer segmentation. Reinforcement learning, we know that from robotics, navigation, games, or autonomous driving. By far, the most important part for us in the relevant for the field of natural sciences is supervised learning. And we will go into a bit more detail here. So these problems here are not comprehensive, there are more, but those are the most frequently used problems that we deal with in supervised learning. So first, sequence prediction. We all know that from large language models. Classification such as email spam detection or medical diagnosis. Time series prediction like Streamflow or weather forecasting, and then regression problems where we can do price predictions or hydrological statistics. I'll go in a bit more detail here by showing some of the most common algorithms that are used in these learning problems. So for sequence predictions, we all know transformer-based models like ChatGPT, but then we see for classification, time series prediction, and regression that neural networks are basically in all problems used, logistic regression, different regression methods, and then decision trees and random forest. So those are pretty flexible algorithms that can be used for many different problems. And today we're going to focus on random forest for regression problems and focus on hydrological statistics. Okay, so what is a random forest? Similar like a forest in the landscape, the random forest algorithm consists of many different trees, but in random forest those are decision trees. And decision trees basically split data into smaller subsets. Okay. So I provided down here some literature that explain how random forest was developed over the years. And now we will just go through a typical example, like with very basic parameter settings that are typically used. And so we start basically the training with random forest training with a training data set. Let's assume we have a data set of 3,000 different streamflow gauges. So we have the target variable, annual average streamflow. So in this example, that table would have 3,000 rows. And then we have explanatory variables. Let's just assume we have precipitation and temperature here. So annual average precipitation and temperature. Now the first thing that's typically done, we split the data set into 2/3 that we use for training and then 1/3 we hold back for testing. So 2,000 gauges here, 2,000 data sets. Let's assume it has a Q average value of about 5.8 cubic meters per second. So the average stream flow across the whole table is roughly 6 cubic meters per second. The first step in random forest is sampling from this data set. That's called bootstrapping. It's basically sampling with replacement. So the algorithm takes 2,000 samples out of this data set and creates a new data set. And just statistically, about 2/3 of the original data is then in that new data set. About 1/3 is just statistically not drawn from this. Then the random forest algorithm starts to split this data set. And this split is done so that the variance, so the difference between the data in that one sample is as low as possible. That means that here, for instance, we have in the left database, we have about 500 gauges with 2.3 cubic meters per second, and the right one, we have 1,500 gauges with 6.4 cubic meters per second. And the precipitation value that splits this data most efficiently is at 600 millimeters per year. Okay, and the more an explanatory variable, here the precipitation, impacts this target variable, the higher is the variable importance. So that's, yeah, we're gonna come back to that later. Okay, and then random forest is basically doing the next split, and then perhaps taking temperature as the variable to split the data, but it can also reuse precipitation again. At the end, the model stops when either no further split is possible, or in this example here, we limit the split to 2. That means now that the tree is completed, and we then have here like 200 gauges with an average discharge of 2.5 cubic meters per second. Now the key importance of random forest is that this is repeated multiple times. Okay, so the bootstrapping again occurs on the source data set, and now we end up with a slightly different base data set. Let's say Q average is 6 cubic meters per second. And then the same thing happens again, just the trees are built and the tree is slightly different than the first one. Okay, and this is repeated again multiple times, and the results are then stored as the trained random forest model. Okay, so we have this trained model with the Q average and the splitting of the explanatory variables, and now it comes to the prediction. So we can feed an information to the model, just saying we have a precipitation of 575 millimeters per year, temperature 7 degrees Celsius, and for each of these values, and for each tree, the path along the tree is evaluated. So in this case, we would end up with 2.1 cubic meters per second. In the second tree, it would be 6.9 cubic meters per second. And in random forest regression, all results are averaged over all trees. So for this example, we will yield 4.5 cubic meters per second. And there is an important point to note and to understand, which is the extrapolation. If we now feed the precipitation and temperature value into the model that the model has never seen during training, like 5 millimeters per year, 28 degrees Celsius, very arid desert conditions basically, the model cannot extrapolate. So it will just follow the path here, end up with about 2 cubic meters per second, which is obviously wrong. And this is known, and random forest just cannot extrapolate properly. Okay, if we see this data cloud here, these points, we see the linear regression, which can, to an extent, extrapolate the trend, but random forest just can't. Okay, so that's important. Coming back to our decision trees, so we still have our testing data, the 1,000 samples that were not used. And this is important to assess the accuracy of the model. So to test our model, we run all these 1,000 data sets through all decision trees. Basically, we evaluate for each gauge what the Q average would be. And we just compare it to the observations and then see how good it performs. Okay, so random forest, what are the pros and cons? Advantages: it's flexible in terms of problems which it can be used. Usually the ratio between performance and computational cost is considered very good. It yields information about input variable, the predictor variable importance, and it's implemented in common programming languages like Python or R. The disadvantages are that predictions outside the training data range is not possible, as we just learned, and it can also fit to noise in the data if the trees can get very large and complex and deep. Now, coming to random forest for our Streamflow metric prediction. So we were faced with the task to conduct an aquatic exposure assessment for pesticide use across New Zealand, and we had to evaluate the indicator, the 28-day Q90 low flow during the application period of pesticides. So these are the red areas here. You can see where we had to evaluate what are the Q90 low flow values. And you can see the blue dots here. Those are the gauges, and the Streamflow observations were just not sufficient to directly estimate this 28-day Q90. So what we had to do was a spatial extrapolation based on this selected gauge data. So how did we do this? First, the data processing. And you remember that random forest has the problem with the extrapolation. So the Q90 values not extrapolating below lowest observations is problematic in our case. So there are different methods to deal with this problem. One is we can use a different method to extrapolate, like linear regression, and just add this information to the training data table. A second, simpler approach is to just add dummy zero flow gauges. So we know at flow accumulation 0, we pick random points here, the black dots, where discharge or the Q90 is 0. And we added this data to the data set. Then, the Streamflow metric needs to be processed so that we get the target variable in the table. Therefore, we compiled high-quality data from 476 gauge-based time series, snapped the gauge to the DEM-derived stream network, calculated contributing areas. Then, of course, you always have problematic gauges, outliers, wrong snapping, so we manually checked for those, corrected some, had to discard some, and then calculated long-term average 28 Q90 Streamflow metrics. And then we have 449 Q90 values, basically all in one table, together with the zero flow values. Now, we also need the explanatory variables because we want to extrapolate. And here we collected variables known to influence stream flow. So those are monthly climate, soil data per soil layer, land use, topography, and some spatial information. So there are two options that you can use to prepare the data. The first one is just calculate average variable value per contributing gauge area, basically just as zonal statistics. The second option is you inherently consider the area of your gauge. So you accumulate each variable along the flow accumulation. This can be done with tau DEM's contributing area tool, and we use this approach to process the explanatory variables. What's important to note, we added a random variable here. So basically just one explanatory variable with random values. And I'll tell you later why that was helpful. Then extracted the data from all the spatial layers at the gauge location for the train test and added that to the table. Then we also need the explanatory variables for the predictions. So wherever we need the predictions, we extracted the data from the rasters and added also those to a second table. Now it comes one important point, which are categorical variables like land use. So random forest regression tries to relate consecutive IDs to the target variable, even though there is no relation. So you can have a land use ID or a land use name, but it inherently has no direct relation with the Streamflow. So what you need to do is to encode these categorical variables. And this is further provided in the code example. I'll not go into detail here. We implemented 3 different encoding methods, which we will see, which we'll hear of later more. So the resulting training and testing data set basically looks like this. So we have one table with 449 rows with the gauge locations. Target variable is the 90th percentile Streamflow during the application period, and the predictor variables are just the accumulated explanatory variable. The prediction data set is also one table with n rows, where n is the number of grid cells with the prediction location. So this can be millions of single cells. The target variable obviously has no data, and the predictor variables is just the same as for the training and testing. Now, applying the algorithm. So the first step is just read the train test data set to the table. Then we do some sensitivity analysis of hyperparameters. So test different number of trees, the complexity of the model, test different random seeds, and optionally test the complexity and the depth of the trees. Then we use an iterative training and testing, typically with a k-fold validation. So that means that you split your data set k times, and random forest is trained for each split. So instead of doing it just once, you do it multiple times. Let's say k is 3, so you iterate 3 times through your data, which means that all data are used for training and testing. So the higher k increases the computational cost, but also the more data is used for training within each split. Typically k varies from 2, where you have 50% for training and testing, but typically it's in the range of like smaller than 12. So we assess then the fit and the plausibility per each of these combinations. Can be done with R² or RMSE or other suitable performance metric, and we calculate the average variable importance per split, per k-fold split. And here, with the variable importance, we remove the variables that are less important than the random variable. And then we run the best hyperparameter setting and select the explanatory variables for extrapolation. And all this is provided also in the code example, which we will later quickly go through. Now it comes to the performance assessment. So this is really quick. We evaluated our Streamflow model just with the correlation against the 1,1 coordinate line, and we compared it with different other approaches that we just tested. Mostly correlation, linear correlation per region, representative streamflow rate per gauge, and random forest outperformed all these more simpler models. Particularly, it performed best for the low flows. Okay, so now coming to the input data importance and prediction. So the variable importance, it's important to note that only meaningful results are obtained if the model performs well. And therefore, it can be considered to remove highly correlated variables. So random forest is typically not that susceptible to use correlated variables, but when it comes to the variable importance, that can be skewed, and you might want to remove extremely highly correlated variables. For the variable importance, typically 2 approaches are used. Again, those are provided in the code example. So it's a default feature importance, which was used here, but also there's a permutation importance possible, where the variable importance is actually calculated on the testing data. This is computationally more expensive, but it's less prone to overfitting. So the random variable is used to select suitable predictors. All predictors with less importance than the random variable are excluded. And we see here that land use and precipitation are the most important predictors, and particularly forest and precipitation in May drive these low flows during the application period in November and March. Now in the prediction phase, we read the prediction dataset to the table, provide this table to the trained model, and run the prediction. Basically, we then have to map each of the predicted Q90 streamflow values to each 25-meter stream cell. So what you see here is the mapped Q90 at the streams, and we spatially cut the stream network at 200 meter 50 buffer around the application areas. And in the example shown here, you can also see that a river basically passes the application area. Okay, wrapping up, what are the main lessons learned? So we used the random forest regression algorithm for a supervised learning problem. Random forest is computationally efficient, easy to learn, and performs well usually. It can't extrapolate, requires hyperparameter tuning and validation, and the explanatory, so the predictor variable importance can be used to understand dependencies between your explanatory variable and your target variable. Random forest is implemented in common programming languages, so it's relatively easy to use. Perhaps this is interesting for some of you. So what's the level of effort? Basically, that was around 40 hours for this example here. So to derive the data preparation was the biggest chunk of work, with around 50% of that. Wrapping the random forest model into the workflow, around 20%. And then sensitivity analysis and results analysis, again, about 15% each. So the computational requirements, the sensitivity analysis, that's typically the most computationally intense part. Depending on your iterations, it can take up to multiple days. And the learning, so when you have just one parameter setting, hyperparameter setting, with these 400 gauges and 17 predictors, that's done within a few minutes. The extrapolation to 25-meter raster, so that's 50% of New Zealand's land area that we covered, that takes about 1 hour then. So I suggest just try it. And with that, we go through very quickly through some small piece of code that I prepared, and basically it's provided for you. So Sebastian will put a link in the chat where you can download the code and the data set. And the data set, since we could not share our data, I just generated a data set. So I asked the new GPT model to generate a data set with average annual stream flow, with some explanatory variables, precipitation, temperature, infiltration capacity, and so forth. I also gave it a hint on what should be the variable importance. Precipitation should be the most important, followed by soil and elevation, land use, and so forth. So it generated the data set that it's provided for you, and also that I ran through the code. So the focus of the provided code lies on sensitivity analysis of the hyperparameters, then model testing through the k-fold validation. It's also conducting a categorical variable encoding and can investigate the variable importance. Okay. So basically, this is the script that you can access. What you need is you need to have these modules installed, which is sklearn, pandas, numpy, and matplotlib. Then the script just contains two functions, like a progress bar printing, which is not that important here, but this function might come in quite handy to encode categorical variables. So whenever you have an object type in your data set, it just encodes them based on 3 different methods. Now down here, this is the main part of the script. So you just define paths and file names. So when you download this, it should run straight away if you keep the directory structure. Here's your data selection. So we have the target variable Q. And then down here, this is testing these different hyperparameters. So testing different categorical variable encodings, and folds, seeds, and trees, the complexity of the tree, different number of bootstrap samples, and then the script just iterates through all these lists here, through all combinations. So in this case, it's about 3,000 combinations. It takes about 2 hours to 3 hours on my computer here. And yeah, basically it iterates through this. Here it splits the data into the k folds, and meaning here where it's doing all the magic, just implementing the random forest regressor and then just fitting the model. Here it's calculating the variable importance, first for the ordinary default variable importance, but also the permutation importance. And then it just predicts the model for the test data set. Okay. Finally, it merges all this together, saves the output to some dotty plots and CSV files, and down here writes and plots the sensitivity analysis results. Okay, I tried to comment everything. Also here some further information, the scikit-learn website where you can read more about the actual algorithm. I found the explanation not very user-friendly for a beginner, so I expanded on some of these keyword arguments a bit. You might find it helpful. Okay, so let's get back to the presentation. I just go through quickly 2 slides through the results of that sensitivity analysis. So what you see here is just the results across these 3,000 different runs. So if we look at the different random seeds, we see, okay, they're relatively similar. So the randomness in applying different seeds is not really a problem or an issue here. The categorical variable encoding, so if we use target encoding or one-hot encoding, it doesn't have an impact here, but this is the case because land use in the generated data set seems to have a very low importance. Okay, if you have a variable which is really important, the variable encoding will matter. The tree depth, so if we have just a tree with one split, it's not really sufficient. We see that the performance significantly declines. But already with 3 splits, the complexity of the data set can be captured already. So, and it even declines slightly as the tree gets more complex, which is an indication of overfitting. Okay, then bootstrapping, 50% of the sample seems already sufficient. So if we just, bootstrapping is here. So if we just bootstrap like 10% of the samples, we have a significant decline in R squared. Okay, so the more trees improve the results. So when we have here one tree, just one tree, the result is not really useful. We just have an average R squared of 0.45, but with 100 trees, we see that the performance levels off. So it's just then further increase in computational time, but no further improvement. And yeah, with a k-fold validation, it seems that here, like doing at least 10 splits of your data set is sufficient for the validation. Finally, the variable importance results. So if the performance of the model is low, the variable importance is meaningless. So you can see it here. If we pick a model which an R squared, which is lower than 0, your variable importance doesn't make sense. Like it just says 50% variable importance for the random variable. Okay, but if we pick one of the best models, which we reach an R squared of 0.76, so we see that precipitation is the most important variable, as we asked ChatGPT to generate the data set. But then we also see that the random variable has about 3% and that the other variable, except for elevation, are in that range. So basically the other variables are not don't have a higher relationship with the streamflow than precipitation. Yeah. So, and also in this case, the variable importance and the permutation importance would lead to the same conclusion. So the ranking of the variables would be the same. So considering that we asked ChatGPT to also have a relation for these other variables, we might have to give it a bit more detailed instructions. Okay, so I hope this webinar cleared some fog in the forest for you. I'm now happy to answer your questions. And yeah, just open your mic or write it in the chat. Thanks so much.
All right, thank you. That was a great webinar. I learned a lot already. We do have one question in the Q&A at the moment. So while the mics are being unfrozen, I will read that off, and that is, what is an ideal scale of the random variable added to verify validity of other variables?
So in my experience, it doesn't really matter what the scale is of your random variable. Like I typically use an integer that is in same relationship than the other explanatory variables. So in this case, it was an integer from 1 to 10,000, where we just take a random value of this integer.
Okay. Thank you. If anyone has a question that they'd like to ask, please just unmute your mic.
I got a question here.
Sure.
If you can hear me.
Yeah,
so
we can hear you.
Good, thanks. And I have a question regarding the feature ranking, feature importance ranking. You mentioned some of the variables are maybe highly correlated for those explanatory variables. And I wonder, this has been a huge problem for us when we were trying to run machine learning for our database.
Yeah.
And because based on my understanding, the random forest randomly picking those variables if they are highly correlated without too much rationale behind it. So I wonder, do you have any suggestions regarding how to treat the variable correlation when you rank their importance on that?
Mm-hmm. Yeah, so what I do is I just run the random forest with all the variables I have available, and I just evaluate the cross correlation between each column, so pairwise correlation between all the columns in your data set. So just do a cross correlation across your full table. And then I just set a threshold of, let's say, higher R 0.7, and I remove all the variables which have the lower explanatory power. So basically I extract the variable importance from the first run, and then I exclude all the pairwise variables which have higher correlation than 0.7 and are lower in the ranking. And then I rerun the random forest again with that reduced set of explanatory variables.
Oh, I see. I wonder have you ever run the correlation checking first and then, yeah, I mean, it's hard to choose which one to remove if you run it without.
Exactly, that's the issue. That's the issue. You have to basically gamble, or you have to, based on your experience, like what you think is more important for your target variable. But then it's kind of subjective. Like you add some subjectivity to your analysis. So I usually let this first decision just pass it over to the algorithm and then make the decision based on that first run.
Thanks.
Sebastian?
Yeah, following up on that question, have you ever tried like a technique for reducing the number of variables, like principle, like PCA or something like that? Or that would be just very hard to interpret afterwards?
Yeah, I mean, PCA is typically, I mean, it's basically another machine learning algorithm that you can use to basically, it's an unsupervised learning algorithm. So you basically check if there is some information you can deduce from your data set. But yeah, typically I don't do that additional analysis, as random forest is quite good in extracting these patterns and actual actual complexity from your data set. So it would be additional work, and in this case I wouldn't have seen the additional benefit. But of course there are points where I also consider running a PCA to reduce the dimensionality of the problem, but in this case it wasn't done.
All right, I think we have another question from, apologies for the name, but Zenu? Unmute yourself.
Hello. Thank you for the presentation. I have a question about the validation. I also do the random forest with the cross validation, but I found some studies saying that the random forests have the techniques called out-of-bag evaluation. So they said that the random forest doesn't really need to do the cross validation because these out-of-bag evaluation have already covered this part. Well,
yeah.
And what do you think? Because in your presentation, in your study, you still do the cross validation.
I do, yeah. So there's a slight difference between doing an out-of-bag validation. So just briefly as an explanation, the out-of-bag validation is basically thing. So the out-of-bag validation is using the part of the sample that is not used in the bootstrapping. So when you bootstrap that first data set, there will be about a third of these data is not used for that particular tree. And then you can predict on these data points that are not included in that particular tree. But the difference with the validation I am doing and this here is that random forest sees this other data in different trees. So when you bootstrap that again, that out-of-bag sample that you don't use in the first tree might be used in the second tree or in the third tree. And then you inherently also use that other data. You don't use it in that one particular tree, but across the many trees it might be used at one point. So that's the subtle difference. But when you run the true cross-validation, the other data is just not seen by the algorithm. So it's a kind of, I would say, slightly harder criteria than the out-of-bag sampling.
Okay, thank you.
All right, we have a question from Emily. Unmute yourself. Yeah, while she's unmuting herself, there is another question in the chat about can you introduce the best resources for the implementation of the random forest methods? That might be a bigger, more general question, but I wonder if maybe we can put a few suggestions maybe in the link that we have where you could.
I mean, I provided some here's some resources. I mean, online you can find many tutorials and examples and also code snippets to use random forest. I found that website here, the Machine Learning Mastery, quite useful. Also, Stanford University has free online courses that are really good. I hope that answer goes into the right direction. If you're asking for for algorithms to implement it, I have so far used random forest just in Python and in R, so mostly in Python. And yeah, just follow up if I didn't answer the question properly.
All right. Emily, you have your hand up. Are you not sure if you are having problems unmuting yourself?
But just type it. Just type it in the chat.
Oh, yeah. You can type it in the chat if you can't unmute yourself. Okay, I think we've got a couple more here. Hold on. No?
I can read another question.
Sure.
And you mentioned that machine learning, the random forest does not extrapolate well. And I see you have multiple predictors in your data set. So I wonder how you define your domain of applicability for your method. I saw you have like 17 predictor variables for that. And then how do you define your interpolation domain and extrapolation domain on that?
Yeah. So what we did is here. Basically, we defined points in the landscape where we, just from experience, we're relatively sure that there the stream flow is 0. Basically a worst case scenario. And then we just extracted all the variables at these locations and fed that information to the table. So basically each of the 17 predictors is populated at these points, similar as if there would be a gauge. Just we give it a known value of 0 for the target variable. And then we run, the algorithm again. You can do more sophisticated methods here, and people are using multiple linear regression to extrapolate your data set below outside your actual data set, and then combine random forest with the regression. So that might produce better results than what we achieved here, but actually we were quite happy with the results already. So we just sticked with that relatively simple dummy 0 flow values approach.
Mm-hmm. Thanks.
Okay. And with that, I think we'll conclude the webinar. Thank you very much, Dr. Kiesel, for the interesting talk. Thank you also to all the participants. And please, if you could take a few minutes just to fill out our 4-question survey, it should be very quick, and send it back to us on future topics and how this webinar went. We would very much appreciate it. Stay tuned for the information on those upcoming webinars through our LinkedIn page at Stone Environmental. And we'll also have another email blast. And many of you probably got that for information on this particular webinar. And that's it. Thank you very much for your interest, and have a great day.
Thanks.